Hello everyone, my name is Samuel Dembowitz and today I'll be talking about Lab 4, Oscillations. In this video you'll see me observe and analyze a real-life system using Tracker, create a computer model of the system using GlowScript, compare the model to the observed system, and describe the physics phenomena involved. The goal of this lab was to implement the energy principle. The change in total system energy is equal to the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring energy. I analyzed the video in Tracker to find positional data, which I then implemented into my GlowScript model. I found the kinetic energy using 1/2 mass times velocity squared, the potential gravity using negative g times mass times h since it's near the surface of the Earth, and the potential spring energy using 1/2 times the k constant times the stress squared. I then updated the total energy, velocity, and position of the data and iterated over the time that the video went on. I then compared the computer model with the tracker data to see how accurate the computer model was. For our system, the weight of the mass on the spring was 0.402 kilograms, and the spring was approximately 0.7 meters long when stretched. Here is a video of the motion that I used. Notice how the spring is going both in the x direction and the y direction. You can see my tracker model here with the calibration stick here and the axes set with the negative y direction downward. Over time I modeled the position using center of mass to get this data here, which is the x data. There's also a graph that I will show later of the y data. I calculated the initial position using the tracker data, as well as the initial velocity being at rest, meaning that it was 0. I found the period to be 1.59 seconds, which I will discuss later, which I used as the average of the x and y periods. Here are the position graphs over time for both the x direction and the y direction. You can see my calculations for the period in the x direction and the y direction here. I used the average period as using one period over the other would create a greater accuracy in one axis while lowering the accuracy in the other. Since the period affects the k constant, the initial length, the spring force, and the net force, I had to split the difference in order to create a more accurate model. To initialize my program, I collected the x and y position data from Tracker as a CSV file. You can see that on the left there. I also included the initial position, velocity, mass, and time range of the motion. You can see the mass, position, velocity. You can also see the constant g, the delta t, the k constant, which I calculated using the period I calculated earlier, as well as the relaxed length of the spring, also using the k constant I just calculated. I then also did the initial calculations for energy within the system using the equations I showed at the goals of the lab slide. Inside the for loop, I had to calculate the force of gravity, the force of spring, the net force, the velocity, and the position of the ball over each time step using the momentum principle and Newton's second law. I then updated the delta energies and energy values themselves to be used in a graph. You can see the video of my GlowScript program in action here. You can notice that the ball is very close to the computer model. The ball is in blue, and the observed position is in red, the one from the tracker data. You can see the x and y position being very close thanks to the average period that I used, and you can see that the sum of the energies is 0, that constant yellow line in the energy graph here. You can see that the kinetic energy and potential energies are going inversely of each other as the ball moves through its system. You can see how the x and y position is very close to the accurate tracker position data. Here's a closer look at the change in energy over time graph. You can see that the delta energy remained at 0 throughout the entire observation period, which means that the energy principle is satisfied because there are no outside forces acting on the system, so the change in energy inside the system should always sum to 0, which in this case, the change in U spring plus the change in U grav plus the change in kinetic energy added up to 0 at every time interval. Here's a closer look at the position over time graphs for the model and the experiment. You can see that they are very close together for both axes, which is a result of the period being the average between the two. If I was to improve the comparison, I would include more sources of energy in GlowScript using heat and air resistance. I would also have a better camera, extended positional values, and tracker to allow for better calculations, as the video was occasionally blurry and the center of mass could be misplaced. Overall in this lab, we learned the implementation of the energy principle. The change in system energy total is equal to the change in the system energy's components. We analyzed the video and tracker to find the period, the k constant, and the relaxed length of the spring. We predicted the motion and energy of the object given positional data I used these kinetic energy, potential gravitational, and potential spring energy calculations, as well as the Newton's second law, change in momentum over the change of time equals net force. This way I could create an iterative loop that calculated total energy, velocity, and position to create a comparison that showed that the glow script model was very close to the real-life observation, and it satisfied the energy principle. Thank you very much for watching.